Evidentemente la cámara first.
Entiendo que grabando.
¿Qué cosa?
¿Cómo se pusiera?
Qué inteligente.
RCD. Arriba a la izquierda. Sí. Para es importante, de verdad. Green, red and blue.
Entonces, pero grabando tiene sentido.
Ya.
So, thank you all for coming. Today, I'm going to introduce you to Fernando Tinaut. He's a solar system researcher specialized in the field of asteroids, actually studying spectra in the near ultraviolet region. And well, he did his physics degree in Granada. Then he moved to Tenerife to study the master in astrophysics in the Universidad de La Laguna there. He worked also in the Observatorio del Teide as a telescope operator. And after that, he started his PhD thesis also in the IAC, the Instituto de Astrofísica, Canarias. As I said, studying near-ultraviolet aspects of asteroids. And he finished his PhD this year in summer, in June, I think.
June.
And after that, he came here because he's moving to France to start his first postdoc in the Observatoire de la Côte d'Azur. So, without further ado, I will let him start his talk to show us what he has done regarding near-ultraviolet studies of asteroids.
Thank you, Marase.
First, yes.
Thank you for the organizer to give me the opportunity to make a stop here between my travel to Nice. So as Morales said, I'm going to give you some hints on what I'm working on. That is the near ultraviolet in the reflectance spectra of asteroids as a tracer of some mineralogical information that is related somehow with the water. I will firstly give proper introduction, as there are not too many people here that works in asteroids, and I really like to make this kind of outreach. So let's begin by the very beginning, that is, what's an asteroid? And by the definition of the IAU, they are small bodies that orbits around the sun or another star or stellar remnant. As we are going to work on the solar system, are going to be small bodies that orbits around the sun. Okay, how small? What kind of objects, right? So we are going to answer the opposite question. This is easier to answer. So what is not an asteroid? Anything that is round or spherical is an asteroid. There are going to be planets, dwarf planets, or other objects. This one is funny because it's Ceres, that is the first known asteroid, but now it's classified as a dwarf planet because it's round. Neither satellites. Anything that orbits another object is going to be an asteroid. However, those two that are Phobos and Deimos are supposed to be asteroids captured by Mars. Supposed to be. They are not really sure, but so those are asteroids that they are not asteroids anymore. And also comets, that you can realize that they are really distinct to other things that could be similar to asteroids, but when they are far from the sun and they are not active, they have not this tail, these volatiles that are evaporating and everything, they really look like rocks. So those are objects that are not asteroids, and everything that is in the middle, so small bodies that are not spherical, that are not orbiting around any other planet, and that have not a high eccentricity, so they have not cometary activity, is what we are going to call asteroids. Here there are some of them. This is Vesta, the largest one. Those are Bennu and Ryugu that has been visited, but some sample return missions. This is the smallest, at least the smallest, a couple of years ago. And this is a binary asteroid. So here we can see that we have a large population and heterogeneity in the shapes, sizes, colors, and composition of the asteroid. So we are going through a very heterogeneous field. When we study asteroids, I used to tell a funny story that I think this is properly explaining why we study asteroids. So in 1992, a ship that were going through Hong Kong to the United States crashed, and he was carrying a lot of rubber ducks in the middle. And years after that, a lot of rubber ducks begins to appear in the coast of Australia, North America, also South America, but also Europe and in the Atlantic coast of the United States. And that allows people, researchers, to understand properly how the currents in the ocean works. So those are our rubber ducks. This is the density distribution of all the known small bodies in the solar system. And we have to explain that. We have to try to order how the things happen in the solar system to explain where the rubber piles, the rubber piles has ended here, and any of them here, and some of them are here also. So what had happened? We are able also to find, okay, this high distribution here is known as the main belt. It has most of the asteroids and the small bodies, at least those that we are able to observe. And it is populated by some objects that form actually somewhere around here. Those are known as primitive asteroids that has been not thermally processed, have not been really altered by some thermal processes and from gravity and everything, and somehow they arrive here. They are rich also in volatiles, in ices, so they have formed after the snow line, but somehow they ended here. How? So we were able to reconstruct all the history of the solar system based on those kind of things. And we now know that the Jupiter, when forms, migrated inward, and then when Saturn formed, stopped the migration, and then both of them goes backwards, making radial mixing and spreading a lot of mass outside the solar system. So knowing the composition of the asteroids, why are they there and where are they, we were able to finally reconstruct the history of the solar system. And this is what we found in the main belt. We find really heterogeneous in composition, because we have here some carbonaceous material, silicates that are going to be related with the crust of planetesimals, and others, for example, metallic ones that are the interior of the planetesimal, and all of them are mixed here. To know the composition of an asteroid from the Earth, we need to have some information that can be taken by telescopes. The first one, the easier, was the albedo. So take the light, remove the sun contribution, and you can see here how we find some asteroids that are really, really, really black, and others that are not. Those are the primitives that has not been altered from the very beginning of the solar system formation, rich in carbon, that's why they are so dark, and those that are more bright are those related with the crust of planetesimals, silicate rich, even some metallic ones. Here, okay, if we made the albedo by wavelength, we are going to obtain a reflectance spectra. This is with what we work, right? How many lights this kind of objects it reflects on any wavelengths is going to give us some information on, okay, here we have a band that is related with silicates, so those are silicate rich. But this one has more silicates, more olivine than this one, for example. However, in those ones that are the opaque, dark, difficult to observe primitives, we have no bands. So the primitive begins to be darker, featureless, difficult to explain what is happening there. If we move to a meteorite, that is a carbonaceous chondrite, that should be formed by the same materials or similar materials than those ones, actually the same than those ones, that could be similar to the others. We begin to see something that is interesting, a huge band, that is in the 3 microns region, and this is opaque by the atmosphere, so we cannot observe from ground-based telescopes. However, it has a lot of information of water, phyllosilicates that are going to be really interesting in our research, and organics. That is also a funny thing to find outside. Okay, phyllosilicates. Let's take a look on how are they formed. So we can find a layer of some metals, that could be iron, or could be other metals, a layer of OH, and this is the important part because it needs warm water, it needs to be in contact with warm water quite a lot of time to form. So phyllosilicates are somehow a tracer of the water. And they have finally a layer of silicates or carbons, silicates. Those are phyllosilicates, so yeah, silicates. And yeah, this is the information that gives us the 3 micron region. That is a more diagnostic band. However, it's not accessible, as I said, by the atmosphere band that is going to occult everything here. After that, we have a really shallow band around the 0.7 micron region that is going to be related with iron-rich phyllosilicates. So phyllosilicates where the metal is iron. And it is related with a transition of the iron, an electronic transition in the iron. So we are tracking here phyllosilicates and then water, but only the iron-rich ones. And then it begins a very strong absorption going through the ultraviolet wavelengths. What is in there? We are not really sure still. Actually, we know something about the meteorites, but we are not able still to relate with the asteroids. And this is what we wanted to inspect in our work here. We know that that should be related with a band that has the center wavelength at 0.2 microns. So from some laboratory spectra, we know that this is diagnostic of composition, as different meteorites have different shapes and depths in this region, in this band. We know that this is also indicative of aqueous alteration in meteorites, again, as it's tracking some iron-rich phyllosilicates, but also is diagnostic of some physical properties of the material. So grain size is going to affect there, and also space weathering is going to affect there. Space weathering is the effect that produces the ion and micrometeorite bombardment on the surface of an atmosphere, a body without atmosphere. So let's continue. How we obtain the reflectance spectra of an asteroid? When we observe an asteroid from the ground, we are going to find, or from any telescope, we are going to find a spectra like this one. And this is going to be pretty similar to the sun spectra, as we are observing the sunlight reflected by the surface. So to know the properties of the surface, we need to remove the sun contribution. And actually, it's quite convenient to observe another star in the same night with the same atmospherical conditions, the same instrument, and to remove the spectra of this solar analog. That is going to read out some information that is from the atmosphere, not from the star, not from the meteor. And this, dividing one by the other, we are going to obtain finally the reflectance spectra. Why is this important? Because we have to really be sure that the solar analog is a proper solar analog and has the same information or the same spectra than the sun. What happened here? What happened here is that since the 1980s, the near ultraviolet in the asteroid science has not been properly studied. So most of the solar analogs that had been used largely since the 1980s were solar analogs in the visible wavelengths from 0.5 to 1 point something. However, they were not working properly in the near ultraviolet wavelengths, let's say below 0.55. So when we revisit some solar analogs and when we go through the Gaia GF3 catalog, we realize that the use of the solar analogs were introducing an artificial reddening in this wavelength that were enough to confuse two different taxonomies of asteroids. So we proposed a correction, we applied it, and we began to study 60,000 of asteroids that the Gaia GF3 were allowing us to study. And the first thing that we found is a nice correlation for some of the taxonomies between the visible, this 0.7 micron band, and the near ultraviolet absorption. So we are kind of saying, yeah, the near UV absorption is going to be related with phyllosilicates. That is, with iron-rich phyllosilicates that are the ones making this 0.7 micron absorption. Another thing that we found, and it is the first time that someone said something about that, is that we found two different beginnings in the near UV absorption. One of the, for some of the taxonomies, the absorption begins at 0.5 here, but for others, it stays flat and then begins the absorption. Those two taxonomies, this one and those one, are related to two different kind of phyllosilicates. So those are not iron-rich phyllosilicates, and those are iron-rich phyllosilicates. So maybe we are seeing more than only iron-rich phyllosilicates. Maybe we are just tracking phyllosilicates and then water. Okay, after applying, this is the last result on this paper on Gaia. After applying dimensional reduction algorithms, we were able to find a gap between those asteroids that presents the 0.7 micron band and those that has not this band. So using and this is the first time that we see this gap, and we are able to differentiate properly those that has the 0.7 micron band and those that has not the 0.7 micron band. So this is telling to us that we are able, using the near UV, to differentiate the asteroid that has iron-rich phyllosilicates or those that has not these kind of minerals. We found also other systematics, as the T types have more albedo, and as the F types are smaller. And this is something that some people were already discussing about. This is unpublished still, but we are working on that. We are increasing our sample. Those are asteroids studied systematically from ground-based telescopes in the Canaries. And we are increasing sample up to 150, I think. All of them are primitives, so it's kind of a good sample. And we have a spectral resolution enough to make some model fitting and try to study properly the near UV absorption. we arrive up to 0.355, I think. So we are not able to find the bottom of the band, but using those models, maybe we are able to infer where is the bottom. By the moment, we are just saying, where is the beginning? And we find, once more, that the F types and the CG types have two different beginnings in the band. One around 0.4 and the other around 0.55. And the next correlation between the 0.7 micron band and the near UV band, or the near UV absorption, is still present here. For the still C and G for sure, P seems also not for the F, that seems to be behaving in another way. Okay, how much time I have?
So in 53, you are about half an hour.
Perfect. And this is now my project, let's say. I moved from primitive asteroids to primitive material. This is a moon of Saturn that is kind of amazing. And researchers, since a century ago, noticed this huge albedo binamality in this moon, as it has a 50% of albedo in this phase and a 5% of albedo in this phase. It is a distant satellite, regular satellite of Saturn, third larger, second older. It is tidally locked and embedded in a ring. So it seems that all this material could be being trapped from the ring, as it is always facing the leading phase to the ring, and it's the same phase. However, the origin of this material is still controversial, as we found differences in the spectra between the particles in the ring, particles in the surface. But numerical analysis said that this shape seems to be from deposits, exogenous deposits. So we decided to use the near-UV data obtained by the Cassini-Huygens mission to inspect what is happening there. We focus on this region, this transition region between the dark phase and the bright phase, as is where the higher spatial resolution data were obtained. So we generated a map, and we have only 4 filters. But we already found some nice differences in the near-UV absorption. We have also this region observed in the infrared, what allows us to relate this absorption to the 3 micron region, that is the more diagnostic lab. When I studied the near ultraviolet slope that I computed in this region, when I studied the distribution of this slope, okay, I'm going to be first here. When I studied the visible slope, I found 2 beautiful Gaussian distributions, more or less. One related with the ices that are around here, all the white things, and another related with the dark material. That's actually with the ice, you are able to see that there are 2 different things, ice and dark material. But when you go through the near ultraviolet slope, you find something that is more complex around the dark material peak, or dark material distribution. Trying to infer what is happening there, we noticed that we had 2 different things in the near ultraviolets when we use the near ultraviolet slope, and we were able to find this bimodal distribution. So now we try to compare with the material that we knew that is supposed to be from the lithosphere of Fe2, so below the ices. That is not exogenous, and we compute the absorption in the near UV, and we find that it is really close to the very beginning of this distribution. We made then a color code with different near UV absorptions, and we plot it in the surface. What do we found here? Firstly, we find a transition from the left to the right, that is from the trailing phase, icy trailing phase, to the dusty leading phase. So we can infer here that something is happening with the UV absorption. Could be mixing with the ice, could be some kind of space weathering. But when we go further, and I'm going to go to this one, in the leading phase, in the leading dusty phase, we find that only the rims of the craters were compatible with the lithospheric material that we observed in the other crater world. So what we wanted to say here is that, or what we are proposing here, this is not published, but this will be soon, is that the exogenous material that is falling in the leading phase of the habitus is covering a lithospheric material that has already there. And this is generating a different spectra in this material, in this phase, when you observe it, the whole phase integrated, than the particles that are in the ring. So this could be the reason why the spectra are not compatible between the dark phase and the Phoebus ring particles. We have seen also that when you look in the material that is compatible with the lithospheric one, you see that the crater interior has stronger absorption than the outside. And this is something really similar to what happened to the, or is really similar to the effect of the space weathering. The space weathering made the bands shallower. So what we could see here is another material that when a meteor comes, extract the fresher material that is below the first layer of dark material. So what we are sure about is that the near UV is a key wavelength to infer the origins and the nature of the dark material in the habitus surface. Those are the main aim of my thesis, is explore extensively and in different places the wavelength region between 0.35 and 0.5 microns to see what we are able to do using the near UV. And that is going to infer how useful is going to be the UV absorption, the whole UV absorption. And what we obtain is that it is related with the iron-rich phyllosilicates, but probably is also related with space weathering and also with other kind of phyllosilicates. And that's all. Thank you.
Thank you very much, Fernando.
Thank you.
Very nice talk. Questions?
How silly one.
Sure.
No silly question.
Yeah. Well, have you read the novel for 2001: A Space Odyssey?
From the 2000?
No, for the, you know, the movies 2001.
2001, A Space Odyssey.
Okay, so which is the question?
Have you read the novel?
No, I haven't.
Okay, so because in the movie they go to Jupiter, the monolith that is covered is around Jupiter, but in the novel they go to Saturn.
Okay.
And the monolith is located around the apetus.
Oh, yeah.
Because the difference in albedo with the two sides was acting like a beacon.
Okay.
So the alien civilization had somehow deposited this dust in there.
Okay.
So an observer from Earth would eventually discover like something weird is going on. So you wanna include some quotes in the thesis of your work or something?
My thesis is already done, but I haven't read it. No.
Yeah, but origin of the dust.
Maybe.
I said it was a silly question.
No, it's fun. It's fun.
Sandra?
Gaia is famous for having very little sensitivity in the blue.
Yeah.
So I guess my first and most basic question is how did you take that into account and how much that affects the core of your result?
Yeah, I'm going to go to my paper. Fastly.
That was a clever move.
Yeah,
to have it
this
open.
one. Let me show you because yeah, we made a lot of cleaning work in this data sample. So firstly, we take only the data points that has no quality flags. So only the best one. After that, we take a look onto the slope in the near ultraviolet versus the signal to noise ratio. And we find that. Oh, it's wrong. Okay. And we find that. So this range of slopes makes no sense in asteroid science. So we decided to reject everything that is below that. We finished with a sample of 500 asteroids. Yeah, from 60,000. Here in this meeting.
Sometimes he has glitches, but I don't know why it's happening in so many.
Okay, so here are only 500 asteroids, where we have the last point in the tutorial. Here are much many more. I don't remember how many. I think it was 15,000, something like that. So even with the blue, we were able to make something because we are seeing the beginning of the absorption.
And if I may, another sort of related question, which somehow since because of J plus,
Yeah.
because of JVAR, we have lots of filters in towards the blue, especially J plus covers that specific range with I may be wrong, 4 or 5 filters,
Actually, 5.
5
Yeah.
filters.
Actually, J plus at the moment is better than Gaia in that region because for asteroids, they published, I think it was 3 filters for that region. It was around 3.
Here they are.
No, not filters, but points, because they did a huge
Kind of average.
rebinning. 1, 2, 3.
4.
You take the open 5?
55. Open 5, there is no filter.
No filter.
No,
So
open
that's it.
55.
In that region, they have 3 points. Well, we have in J plus 5, I think. From 0.5 down to 0.37.
And JVAR we have 3 ones,
That is
We
going to
are
be
in
kind of
J-bar,
same.
we can do the same thing as
but deeper. No, we actually can do the same things as that.
problem is that we have less objects.
Because we are farther away from the clip.
That still is going to be interesting to add more and more objects. We are able to cover these regions. As much as we have, it's going to be better, for sure.
Yeah. This is only marginally related to your work, but I have the curiosity. So,
Sure.
Anyway, many minerals, when they are exposed to UV light, they show fluorescence. So, have you ever seen fluorescence bands in the spectra of asteroids?
No, actually, fluorescence, people in planetary science that is seeing fluorescence actually in the UV should be related to atmosphere things. The amount of light, the UV light that arrives to the surface of an asteroid is quite small. So I think it's not enough to make them bright. I'm not sure, I don't know the numbers, but still low reflectance, small amounts of light, I think that they don't are bright.
Okay, then something related. That bright spot that appeared in series a few years ago,
Yeah.
what was that in the end?
It was nice because it's quite interesting because it's like yeah, there are a lot of salts there, but generated for somehow cryovolcanism. So an ocean that is below ocean, it's not actually an ocean, but water that is around there, and that for pressures and things begins to pop up, generating there is amount around. I'm not sure if it's one. There is amount that is generated by the pressure of the water going up and generating a volcano from water in this semester.
A geyser.
But those are salts.
Nice geyser or something like
It
that.
should be something like ice, so more dense than water itself, but it's not going to be that far. But yeah, some geology that happens still in cold bodies.
And they discovered some fog in the craters that have those white spots. It's like something is evaporating there.
Yeah.
I wanted to make a comment actually. Anybody? The current theories about the formation of the moons of Mars is more like a giant collision ejecting material from the planet, not captured asteroids. It's like it happened very early and generated more moons. Most of the moons crashed back into the planet, and those were remaining.
This is the last thing they
The
said.
current consensus, I think, it was that because the composition was more similar to the mantle of Mars than to asteroids.
If I remember properly, I'm not sure, Morata, correct me, but I think that one of those still, I'm not sure which of them, is kind of similar to comets. You know?
There was
I think that I read that somewhere. Not sure. Yeah, could be.
Alessandro first.
Two things. One, actually, since you're already on this slide, if you go to the following one,
This one or the other?
yeah, this one. So, so basically, you're saying that one of the differences between comets and asteroids is the eccentricity.
Yeah.
Why?
Yeah. Okay, it's not actually that. It is what eccentricity generates on the asteroid. So if it is close, it's not eccentricity, but the orbit characteristics. If it has a high eccentricity, it's going to go farther. So it's going to be more time far from the sun, and it's going to retain some volatiles.
Okay.
And when it goes closer, it's going to be an object that is going to be easy to differentiate from an asteroid. So that was the first thing that they made. However, when you go to asteroids that have kind of moderate eccentricity, you begin to see cometary activity in asteroids. So where do you put the limits is going to be the question.
Somewhat related with orbital elements. Most of what you discussed, it has to do with the taxonomy, it has to do with the distance from the sun. What about the elevation distance from the ecliptic?
Okay, difficult question. I think that I don't have any graph to follow that. So, if you go to different inclinations, you find okay, the location of asteroids in the solar system has some things like this one that you were going to see. What's that? This is resonances between planets. And then you find something, no, not this one, but when you have here inclination and say major
It's
axis,
similar.
yeah, it's something similar like
Feels
this
like
one,
that.
but it's not this one.
It's any major axis versus inclination.
Yeah, if you plot here inclination, you're going to find something similar than this, that is also related with resonances with planets. So that you have an inclination that with this period
It's a
should
few
be
slides after
in a
this one.
stable orbit. Huh?
It's a few slides after this one.
No, I don't have this one.
I think you do.
Well,
Oh, no, that one. Okay,
it's
yeah.
similar.
But
Yeah.
without the resonances one.
Yeah, but it's still what you find is something like that. Where I could say is that in different inclination we have different collisional families, so different materials. But it's more related on which was the parent body that was there and collide and then disrupt and generate this family of objects.
But regarding that question, this is something I tried to do during my thesis, trying to check if there were different compositions depending on the inclination. And with the data that I had at the moment, we did not see any. The major difference in composition comes from the distance to the sun.
Yeah.
Might be, but for example, Vesta, which is in the middle of the inner main belt, has a totally different composition. Well, not totally, but in that region, there's a mixture of primitive objects with silicaceous objects, and is Vesta. Then you have, for example, in the outer part of the main belt, some objects that are Vesta type, which at the moment we do not know if they came from the inner part of the main belt, if they appear there because of how things originated in the solar system. There are questions that have to be answered. But regarding that exact question, at least as far as I know, there are how to say this? The differences in composition are not noticeable versus inclination. So basically, versus distance to the sun, say major axis. Thanks.
Elena?
Yeah, I'm going to change topic a little bit. I'm not familiar with asteroids, so thanks a lot for the very nice talk and introduction. I was curious about how rotation or velocity could affect your measurements.
Let's go through Rio and Benu. Yeah. For example, this is one thing that is affected by rotation. Actually, as we get closer to those, it's quite easy to see. This diamond shape that we can find in those two asteroids is because they are fast rotators. Well, actually, not fast rotators, but moderate fast rotators. And then material that's here go out because of the rotation and goes there. So here you are going to find fresher material here, older material here, something like that. It's going to affect to the age of the surface. It's going to affect to the shape. It's going to affect somehow to the spectra from ground. But still, we're going to find different materials. There were in the last year or in the one before an asteroid that disrupted, broke in multiple parts because of the rotation. And also, the rotation is going to affect your spectra if you have, it's going to be here, a big boulder, or best I think that it has a huge crater that changed slightly the spectra of the asteroid. So yeah, rotation effects. And this is one of the problems that we had with J+, and is that we observe different filters in different times. So we are seeing different places and different amount of light, and it was kind of difficult to infer which was the original spectrum.
That's one of the things we have discussed.
Yeah.
But the point is that, for example, if the asteroid is not completely round, if you are observing different non-contiguous filters, one after another, maybe as he said, you are getting less light, then it will affect the shape of your reflectance spectrum.
In this one, for example, imagine that it's something like that. You are going to have a lot of light that is reflected, but half an hour or 2 hours after that, you are going to have a few light reflected. So it's going to drop, not because of the composition, but because of the shape.
So but you can see the other way around. You can get a lot of information from
the shape. Yeah. But for that, it's better to use the same
position.
Rotation periods are of the order of hour.
It depends. We have seen some of them that are minutes, but they are one block, one metallic or silicate block, not like those.
I think that the mean rotation time, according to the light curve database, it was around few hours.
Yeah.
Of all the objects that have periods calculated, it was around 5 hours or so. So in principle, it should not be affecting your measurements, but it can be. Actually, this is something that this Carvana, I was trying to correct the data for J+ for this kind of light rotation.
Properly for some of them.
For example, in J+, we observe all the filters according to their wavelength in a continuous way. This does not affect that much. It's like auto-corrected.
Okay.
J-bar is well thought.
J-bar is
incredible.
I have more, maybe a technical question. How critical is the I mean the calibration with the solar analog, in the sense of how critical it is to get the observation close to your close to your field, close to in time and space to apparent distance to your object, and whether if, as long as you have a good calibration on your asteroid and your analog, you can use it from other sources, for instance.
No, we are now, when inspecting those asteroids that we observed from ground-based telescopes, and we observe a lot of stars, trying to make sure that we take the best one. And we are having some troubles even observing the same star in the same night. So you observe the star now, and 3 hours after that, the atmosphere changed, the absorption in any part of the spectra change, and it's going to be affected. Also, we have the reddening because of the air mass, so it's going to change. The best is to observe close and in time and in distance in the sky. Is the best. Also, the near UV is kind of tricky because it's noisier. I don't have anything to show. You see that the same spectra here, you're going to have more troubles. So you have to be very careful on the star that you're using and the quality data.
Yeah, but I guess your results may change, no?
Yeah. Actually, I have not this paper here yet, but in one of the paper we revisited some spectra from my supervisor, and we noticed that the stars that they were using were not the proper ones, and we remade the calculation with a star that were observed also those nights, making a ratio and all that, and suddenly the results changed the taxonomy, and the taxonomy makes sense for the very beginning. Yeah. So yeah, it's something that we have to be very careful, and I try to say to the community that, okay, be careful when you go to the UV wavelengths, because it's tricky.
Could you use the reflection on satellites to get the spectrum of the sun?
I try to propose that a lot of time. Anything adheres to me. Because we know how the solar planets reflect. We have the spectra, the reflectance spectra. So now that we have a lot of asteroids, satellites around, could be good to
difficult to track them, but if you take one that is very bright and crosses the...
If it crosses the slide, it's going to be enough, because they're bright, kind of bright. So
I need to repaint again the
starting.
Please don't make them black anymore. Now we want at maximum reflectance.
But do we know how the antenna reflects? Because most of the light on the Starlinks is the surface.
Yeah, I know that for the Starlink, that is, I mean, if you take a spectra in ground in a laboratory control spectra of that, is going to be enough to make a proper correction. Using the sun at the same time, that is also a thing, because the sun going below that, it begins to change from time to time. So yeah, it's something that could be interesting.
Hi, I have a question about the later part.
Okay.
Thank you, by the way, by the talk and the answers. This has been fun. So if you stop at the images that you were using, so I was wondering, do you have to make a correction, now that you were talking about the rotating asteroids, do you have to make a correction about the shadows within the craters, or are the images in the different filters taken at the same thing? And that, I don't know, I'm surprised.
It's totally right. Okay, from those images that are taken by filters, they make 4 filters in a row very fast. And that's why they only take 4 filters. They have a lot more of filters, and I was able to compute other things with lower resolution. So in each square here are 4 filters in a row. That makes things easier because I'm measuring ratios between filters. So where there are less lights, it's going to be less light in both of them. But still, you have to correct the incidence angle of the sun compare with the emission angle on where you are and all of that, but there is some calibration pipelines that make them using the best topographic measurement of the moon that are not really, really good, but they are good enough. You're welcome.
No, I'm happy now.
More questions?
I have one that might be for Morate instead.
Go ahead.
So I was wondering, like, do you think JPass is viable at all to make this kind of association, or would it require,
I'm leaving.
or would it require a dedicated open time program with the number?
Actually,
That you should present.
I was talking before with Alessandro because I'm wondering about how can we use some of the traits in JPass, maybe just to track the near ultraviolet region, for example.
Maybe a single trait may be useful.
I think that
Maybe
maybe
enough.
just one. I'm thinking about the project.
Because changing, I was thinking on changing traits very fast and like,
I don't think it's good enough.
Sandoza's not here.
I'm planning about a pilot project trying to use JPass at least to get information this week. Because if we manage to, I don't know how many filters do we have in just one tray directed
4 blue ones,
for blue
for in
ones.
the blue and the others
and the rest are red.
distributed.
It's something that I think it should be done, but it's going to be some how do you say directed project pointing to some places in the ecliptic to get a high number of objects. But I think that's something we should at least try.
We'll be very happy to see those data. Because there is anything in the near view for asteroids. So, as much as it's games, there are things to say for sure.
Yeah, that's it, because it's not a very studied region, at least at the moment. So yes, we should try.
Gaia is going to open the epoch spectra of asteroids in spring of 2026. And there you are going to be able to bin in the spectra where you want.
So they're going to release the full prospect.
Tier 4.
Tier 4.
Speaking of which, what about real ultraviolet? The ultraviolet that one can do from space.
Yeah,
No.
I have no graphs here, but still we have the problem that the sun emits few ultraviolet and the asteroid, carbonaceous asteroid, reflects few
Okay.
ultraviolet. Because we have that the sun spectra, where is the sun spectra? Here. Sun spectra gets lower here, and the asteroid reflectance it's lower here, and we are measuring a drop in reflectance. So yeah, very few amount of photons. So they are spectra from HST that are quite noisy, but still you are able to see that around 0.2 begins to turn up. So around there is the minimum of the band. For the point here is that they observe only those C and P. Because this classification came from Fallen from the 1980 something. And after the UV is missing, we miss G and F. And G and F has a lot of things to say when you use the nearest one. So this is my next step. I really would like to take Hubble before it dies and try to obtain a spectra of the F types and also why not a G type. Yeah.
Hurry up.
Yeah. This year, hopefully.
More questions? Okay, no? Let's thank the speaker. Excuse me.
Una pregunta, pero es más para.
Es que quería hacer yo también. Tengo una pregunta, pero es